Okay, everybody, so in this video, we'll be talking about optimization problems. And in order to explain what that is, I thought I would start with a very simple example. As far as this goes, I don't think that problems get any simpler than this one, so I think if you were going to start off on the right foot and understand what's happening in this lesson, this is a good place to begin. So, the question goes like this. What is the maximum area that a rectangle can have if its perimeter must be 20 feet? So notice here, it doesn't just say what is the maximum area that a rectangle can have, because I guess that's like asking how big is the universe. All right, there's nothing limiting the area of the rectangle. But if its perimeter must be 20 feet, that will limit ultimately how big this rectangle can be. Okay? All right, so there are two ways that we can solve this. Of course, I have to be, in our class, I have to be partial to using calculus, but I think it could help you understand what's happening if you look at this method of making a table. So here's what I was thinking. Why don't we go through some of the possibilities for this thing? In other words, what are the possibilities of a rectangle if its perimeter is 20 feet? So here I've listed some possibilities. This is not every possibility that there is, but it's enough of them, I think, to find the answer. All right. So every possibility I mentioned has a perimeter of 20 feet because that was the constraint that we're working under. But it could be a 1x9 rectangle. Why is that? Well, the perimeter is the total distance around the rectangle. So 1 and 1, that's 2, and 9 and 9, that's 18, and 18 plus 2 is 20, all right? So twice the width plus twice the length is 20 in that case. So a rectangle could be 1x9 and have a perimeter of 20. What would the area be? Well, the area is the product of the sides, so the area would be 9, okay? And in our case, I guess it'd be proper to talk about the units, 9 square feet. Another example, it could be 2x8, right? The perimeter is still 20 there. Okay, you can add it up. Twice the length plus twice the width is going to be 20. And then the area, though, is 16. So what I noticed is I opened up a little bit more space on the inside of it. I made it a little bit wider and a little bit less long, and I opened up more area inside of it. Okay, now let's just keep going. We'll see if there's a pattern. What's a 3x7? 3x7 rectangle has a perimeter of 20 feet, and the area is 21 square feet. A 4x6 has an area of 24 square feet. And I'm noticing a pattern that the wider I make it, the more space I open up on the inside. Does that pattern continue? A 5x5 rectangle has an area of 25 square feet. A 6x4 rectangle has 24. So now I kind of see the trend. As we started from this one, with the width of 1 foot, and we gradually opened up more width, the area got bigger and bigger and bigger, and then past a certain point, it will start to decline again. 6x4, 24 square feet, 7x3, 21 square feet. We're just going to get, obviously, all those values all over again. So it looks like, this table is not a definitive proof because I don't have every single possibility listed on here, but it appears that that's the maximum. That of all the rectangles that have a perimeter of 20 feet, that the biggest that it could possibly be has an area of 25 square feet. Okay? So, all right, now I'm going to offer that up as an answer to this one. All right. Okay, that's certainly what it seems from the table. Now, all right, so that's kind of a brute force approach to getting the answer. It's definitely not foolproof, okay? But it might help you understand a little bit about what's going on. So let's talk about how a person would use calculus to do this. So using calculus will involve, at the most basic level, using functions to describe what we're working with. and possibly using a derivative somehow or exploring the nature of the curve somehow. So how about this? How about I'll call the width x and the length y, and I'll formulate the problem like this. I want to maximize the area, right? And the area is the length times the width, but in my case, I'll say it's x times y, as I've renamed the variables width and length with x and y. And there's a constraint though. It's not like we're just maximizing the area. There's also something holding the area back or constraining it. So I'm going to say that we have something else called constraint. Okay, and the constraint is that the perimeter has to be 20 feet. So, all right, how are we going to express that through an equation? The perimeter of this shape must be 20 feet. Well, the perimeter is twice the width plus twice the length, and then that needs to be 20. So the way we think about it is we're going to maximize this subject to that constraint. Okay? Now, without me elaborating much on the procedure at this point, here's what the procedure is. How did we find maximum and minimum points on the curve when we talked about the first derivative test or the second derivative test? Those came from points on the curve, just to put this in very rough terms, where the derivative was 0. Okay? So I need to put this thing I'm trying to maximize into some single variable function. Over here I have two variables, x and y. I need it to just have one. And then if I found the derivative of it and set it equal to 0, it would take me to my answer. Okay? So we use the constraint in there to reduce it to one variable. Then we find the derivative and we set it equal to 0. That's the procedure. So let's work on this in a way that we can substitute it in there. So if we divide by 2, could we say that x plus y is equal to 10? Okay, so we could do that. And then could we solve this for y? Yeah, we could say y is equal to 10 minus x. All right. And then could we take that and substitute it in here and reduce that to just be a function of x? Yeah, we could do that too. It would be that the area is x times 10 minus x. Okay. Now, from here, if we find the derivative and set it equal to 0, it will take us to our answer. It will find us this maximum value. Now, for me to take the derivative of this, I think I'm better off if I multiply all this together. So I'll do 10x minus x squared. All right, and then it's not hard at all to find the derivative of that. That's going to be 10 minus 2x. All right, and I'm going to set that equal to 0, and I'll get that x is equal to 5. Okay, so 5, what's that mean? It means that the width, x, should be 5 in order to get the greatest possible area. So we'll interpret this number this way, okay? So x, the width, should be 5 feet. What about the length? Well, what is the length? What's the connection between the width and the length? Well, twice the width plus twice the length is 20 because the perimeter is 20. But that's the same thing as x plus y being 10. That's the same thing as y being 10 minus x. So if x is 5, that means y, the length, is also 5. Okay? And then what is the maximum area? Because this number is related to the maximum area. So, well, if the width and length are both 5, the area would be 25. And so our maximum area possible in this case, if the perimeter is 20 feet, is 25 square feet. So there would be my answer. All right. It took some inference from that, but, you know, it was in our equations that we were working with, okay? Now, that's the same thing I seemed to come up with on the table, that a 5 by 5 rectangle fits into our constraint of having a perimeter of 20 feet, but that's the one with the maximum area, all right? So I would like you to see that these two are, although they're very different, at least right now in this problem, they're in agreement with each other, okay? All right, so I guess this is the methods on the table. I'm not saying that you can't figure out some other way to do it besides what I've showed you, but as far as our lesson goes, this is what I want to consider. Now, for this problem, okay, I need to take a more detailed look at it. All right, so I want you to think a little bit deeper into it. Here's my more detailed look. Okay, so the problem that we were just doing was to maximize the area of a rectangle whose perimeter must be 20 feet. And I wanted to show you what's happening behind the scenes a little bit and give some more explanation. What we have here is an area versus width curve. When I put that area right there in terms of x only, I'm tracking the area as a function of the width. And it looks like this. It has that kind of shape to it. There is, in fact, a point that's at the top. There is, in fact, a maximum. That's what we were trying to find. Okay. We found that if the width is 5, then the maximum area would be 25 square feet. Now, what it really comes down to then is we're finding this, I guess, a relative maximum on the curve where the first derivative is 0 and the second derivative is negative, meaning that the first derivative is 0, but the curve otherwise is concave down. That's what the second derivative test tells us, all right? So let's elaborate about this a little bit, okay? All right, so I found a prime is 0 if x is equal to 5. That alone doesn't prove this point is at the top. It doesn't prove it's a maximum. We also have to prove that the curve is concave down and not concave up. So the second derivative, that should be a negative number. Let's go ahead and put that to the test to make sure that that's true. So let's see. Here's a prime. A prime was 10 minus 2x. Okay? So a prime was 10 minus 2x. And that makes a double prime negative 2. Okay? Negative 2 is less than 0. So that proves that it is concave down. And that the point is a maximum. All right. So that's a little bit more detail into the procedure, but I want you to think that every time that we do this, there's some curve out there that we're just trying to use the procedures that we've already learned about to find a relative maximum or minimum point on the curve. That's what these questions are going to come down to. When we say we want to optimize something, that we're saying like under some constraint, we want to maximize or minimize whatever we're dealing with. Okay. Now let's do another one that will seem quite a bit different than this one. Okay, so this problem will read as follows. Suppose that there's a cylindrical container and our constraint is such that it can have a maximum combined length and girth of 111 inches. Find the dimensions of the container that's like this that has a maximum volume. So, you know, the fact that the combined length and girth can only be 111 inches, that will limit how big this thing can get. And we just want to find the maximum volume that's possible with the constraint. Now that's really just like that first problem. This shape is three-dimensional. It's a little more complicated. I don't think at all that making a table is going to get me the answer because I think it's not simple enough to approach it like that. But I want you to think that no matter how I do this one, the same kind of thing is happening in that first problem that I showed you, all right? Okay, so let me frame the problem like this. I want to maximize the volume of this container, okay? And the volume of a cylinder is V is pi r squared h. R is the circular radius, being that, let's say this cylinder has circular cross sections to it. The top's a circle, the bottom's a circle. It's like a can, in other words. So pi r squared, that would be the area of that circular top or bottom, and then times the height, that gives me the volume. So I want to maximize the volume. And it says that the combined length and girth has to be 111 inches. So that will be my constraint. And so here, first of all, the length is just h. Okay? That's this part of it. The girth is the circumference around it. All right? So given that this is a cylinder, and it's got these circular cross sections all the way through, and the top is a circle and the bottom's a circle, that means that the girth of it, the distance around this 3D object, is just the circumference of that circle right there, or this one down here, both of which have the same radius. So the circumference of a circle is 2 pi r h. Okay? Oh, I'm sorry. What am I saying? 2 pi r. The circumference of a circle is 2 pi r. So that needs to be 111 inches. Okay. So there. We've got something kind of like the last problem. I want to maximize something, volume, and I have some kind of constraint that was given there in the problem. Now, all right. What do we say that we would do? That to maximize this would just come down to saying, well, v prime is going to be 0 somewhere, okay? But I need to reduce this to having just one variable. So that's where my constraint comes in. All right, so here's what I'm thinking. We can take this, and it's fairly easy to solve it for h. Right? I'll just subtract 2 pi r from both sides. And then I can substitute that in here, and then that will be a function of only one variable. It will just be a function of r instead of r and h, as it is now. And then I'll work on the derivative of that and set it equal to 0. So let's see. If I do that, here's what I'll get. V equals pi r squared h. H is 111 minus 2 pi r. Okay, there we go. Now, I'm going to, from this, need to work on the derivative like that. So, when I get to this point, this is when I'm really thinking, okay, so I got to find the derivative. I got to set it equal to 0, okay? But I think, in this case, I should probably multiply together in order to do that. I should distribute this along that parentheses. So v is equal to 111 pi r squared, okay, minus 222 pi squared, okay, r to the third power. All right. Oh, what am I doing? I'm sorry. I'll get there. So 2 pi squared r to the third power. Okay. There we go. So yeah, from this, I'll find the derivative. Okay. So v prime is going to be 222 pi r, okay? And then here, minus 6 pi squared r squared, okay? So here, I'll bring down the 2 with the constant, 111. I'll get 222 pi. Here, r is the variable. 3 out here with 2, 6 pi squared, and then r squared. Okay. So at this point, I will solve it for 0, now that I've found the derivative. Okay. Now, let's do this. To solve this, let's factor out r and pi. Okay? We could also factor out a 2, but I don't really think there's so much advantage of that. So let's just, or why not? Let's factor out the 2. So 2 pi r, okay, that's what I can factor out of both of these. So I'll get 111, okay, pi r minus 3 pi r. Okay. Right? So that's 222 pi r and then 6 pi squared r squared. Now, because these multiply to be 0, then either this is 0 or that is 0. If 2 pi r is 0, that tells me that r itself is 0, and that's not a meaningful answer to our question. For this other one, if that is equal to 0, 111 minus 3 pi r, then that could be solved for 0 pretty easily, as r is 111 over 3 pi. Okay? All right. Now, that number, well, so 3 into 111, so I think that does work out to, so it's 37. So r is going to be 37 over pi. All right, so that's what the radius should be in order to get the maximum volume. Now, let's say the question is asked specifically like this. So say we want the maximum volume. Okay, we want this thing to be as big as it can be with the constraint on the length and the girth. Okay, and suppose I just ask well, what's the radius? What's the circular radius supposed to be? And what's the height supposed to be? All right, in order to get the maximum volume. Well, in doing this, I found the radius. Okay, it's 37 over pi. Units, that would be in inches. In the height, well, okay, where's the length between the radius and the height in order to find the height? That will be right here, okay? You know, the height plus 2 pi r has to be 111. That was from our constraint. So now that I know this one, I can go up there and I can tell you what the height needs to be as a result, all right? So anyway, let's do the math on that. If I put 37 over pi in there for r, the pi's will cancel. So I get 111 minus, so let's see, 2 times 37. So I'll get 37. Okay, so the height needs to be 37 inches. And then there's our dimensions to give the maximum volume. All right, so I think I want to write it something like that. That would be my final answer if the question was asking for the dimensions, the radius and the height. So we'll get the maximum volume at those dimensions. That's as big as the shape's going to get if we do it that way. All right. Okay, so let's do another one. Now from this point, I've showed you the basic concept with my first problem, right? And then now this one, same concept, math a little bit harder. Okay, and now I just want to play on that theme a little bit, do different kinds of questions. All right, so here goes with this one. Which point on the line is closest to the origin? All right, which point on the line 5x plus 1 is closest to the origin? So how about this? This one sounds a little bit visual, so I'll put a graph. The line 5x plus 1 is a line that has a y-intercept of 1 and a slope of 5. And so it would look, I won't draw it perfectly to scale because I don't think that would really help in this case, but there it is. Something like that. Okay, so there's y is equal to 5x plus 1. And the origin is here. And then there's some point on that line where this distance from that point to the origin is as small as it can possibly be. Okay, so that's how I understand this problem. Now you could imagine that if I put the point out there, well, that would be a lot further away. And if I put the point over here, that would be a lot further away. So yeah, maybe somewhere over here that it's going to be as small as it could possibly be. All right. Okay. Now, so let's do this. Let's talk about how you measure that distance, because that's what I want to minimize. I want it to be the closest. Okay. So real quick, let's do, like, I guess I could call this review. How do you find the distance between 2 points on, say, graph paper or on the XY plane? The distance between 2 points on the XY plane is, well, we subtract the X coordinates and we square them. We add them together with subtracting the Y coordinates, which are also squared, and then we take the square root. There's the distance formula. So that's the distance between points, just in abstract form, x1, y1, and x2, y2. All right. So whatever those points are, you take this x coordinate minus that one, you square it. You take this y coordinate minus that one, you square it. You add them, you take the root. That's how you find the distance. Okay. All right. So that's going to have to be involved in this somehow, because I want to put this point as close as I can to that one. And by close, that means that the measurement of the distance between the points is going to be as small as possible. All right. So yeah, we need to get that on paper, or at least for me to remind you of it before we can get too far into this one. Now, about this point is the origin, so it's 0 and 0. This point is on that line, and so that means its x coordinate is, well, let's just say x, since we don't know where it is. If we knew where it was, we'd have our answer. And its y coordinate is 5 times the x coordinate plus 1. So we'll do like 5x plus 1. Okay? So I'm going to minimize the distance between these 2 points. All right? So I'm going to minimize that. I want them to be as close as I can. All right? All right, so in other words, that will turn out to be this. Minimize d equals root. Well, what is the distance between those points? Root x minus 0 squared plus 5x plus 1 minus 0 squared. There's the formula that measures the distance between them. I want to minimize that. Okay. What will minimize that? What will that involve exactly? Finding the derivative and, figuring out where it's 0, right? You know that by now, though. Okay, so let's do a little simplifying of this before we really do any serious work with the derivative. So let's see. I can say d is equal to, well, okay, x minus 0. That's just x. So let's say that's going to be x squared. 5x plus 1 minus 0. That's just going to be 5x plus 1. Squaring that, well, that will get me 25x squared plus 10x plus 1. Okay, so that's what I'll get as far as the algebra on the inside's worked out. I could add some like terms in addition to that. So let's see, d is equal to, well, let me do one more thing. We're going to end up taking the derivative of this. Let's write that root as a power. So let's say 26x squared, all right, plus 10x plus 1. All right, to the 1/2 power. Now that's as reduced as I want to get it for the sake of finding the derivative. At this point, then I'll find d prime, which is the derivative. Okay, so let's see, that would be 1/2, and this will be by the chain rule, 1/2 26x squared plus 10x plus 1 to the minus 1/2 power, and then here 52x minus or plus 10. All right, the derivative of that interior part, the u part from the chain rule. 52x plus 10. Now, let's do a little bit of simplifying. Okay, I noticed that I'm going to have a 2 on the bottom and the 5x plus 10 on the top. And I could factor out a 2 from that. So I'll go ahead and do this. 2 canceling with 2 factored out of this, I'll get 26x plus 5. Okay, and then that will leave this expression down here, 26x squared plus 10x plus 1 to the 1/2 power. All right, so there's my derivative. My goal from the beginning was to find that derivative and set it equal to 0. So I'll do that now. I'll set it equal to 0. And a fraction will be 0 under this condition. Say just generically, in totally generic terms, a fraction, a over b, will be equal to 0 if that top number is 0 and that bottom number is not 0. Okay, that's how it works. So for this, as long as that top part is 0 and the bottom part isn't, then I'll get my answer. I could also just multiply both sides by that, and it's going to 0 out over here. That's another way you could think about it. But no matter how you think about it, it just takes you to this, and then it takes you to this. Okay, so that's my answer. And it tells me that the x-coordinate of this point needs to be negative 5 over 26. Okay? All right, so my point on that line closest to the origin has an x-coordinate of negative 5 over 26. It has a y-coordinate. Well, you put the x in, you get the y. So let's say the y-coordinate is going to be 5 times the x-coordinate, and then plus 1. So that's negative 25 over 26. Plus 1. So that's negative 25 over 26 plus 26 over 26. That's 1 over 26. So the y-coordinate is 1 over 26. So my picture, it wasn't to scale or anything like that, but, it was roughly correct, and you can tell that the point needed to be somewhere over there, like left and up, all right, left and up. X-coordinate's negative, y-coordinate's positive. Obviously, putting it anywhere out there or anywhere out there puts it further away, and somewhere there in the middle, it's going to be as close as it can get to the origin. Okay. All right, now let's do, for this video, I'll do one more, and then I have some other problems in mind that I need to show you, but I'll make part 2 of the video to show you those. So let's do this one. Okay. All right. Now, so in this problem, I'll have to tell you a little bit about the description for you to take everything in. So suppose that there's a water, like a lake or something, a coastline, and there's land. And you're just going to have to humor me a little bit here and not wonder too much about what kind of crazy situation would this be. But suppose a man is out on the water in a boat, and he's 2 miles from the shore, and he's going to row in a straight line to some point on the coastline. And from that point, he's going to walk to this other point. And let's say that he can row at 4 miles an hour and he can walk at 4 miles an hour. Okay? Which that seems kind of like a fast walk to me, but you're going to have to humor me, remember? All right. Now, so where should this point be? Where should he row to on the coastline to get from the starting point to the ending point the fastest or in the least amount of time? Okay? One more detail. It's 7 miles from point A to point B. All right. So that's the question. If you want to take a minute to take that in, let it sink in. You can pause the video, of course. It's a video. You can always pause the video, but that's the situation. Okay? Now, I want to redraw this with a little more detail. Or let's do like this. I think I can fit what I want to fit on there. If it is 7 miles from point A to B, that means this distance and that distance have to add up to 7. And if they have to add up to 7, then this distance is x from here to here. And then this distance is 7 minus x from here to there. Okay? All right. Now, I want to minimize the time. All right, so my goal on this question is how to get from the start to the end, all by minimizing the time it takes to get there. Okay? All right, all right. So, yeah, I said how do you get there the fastest? That means I want to minimize the time. Now, how about this? Since I know how fast the person can row the boat and how fast that they can walk, all I need to know is these distances. Okay? Because isn't it true that distance is rate times time if your rate is constant? And so that means time is distance over rate. So I can figure out the time to get from here to there and the time to get from here to there by taking the distance, respectively in each case, and dividing it by how fast you're going to be traveling that distance. Okay? So, all right, let's do this. I'll update this picture a little bit. I'm afraid I've crammed too much detail into it up there. So I'm going to have to draw it again in order to show you what I want to show you. But it's, something like this. Okay, so that was 2 right there. Straight line distance to the coastline. This was 1. And this was x. And this was 7 minus x. And what's this distance? That's the distance on the water. Well, we can use the Pythagorean theorem to figure out its root, x squared plus 4. So that's the distance along the water to this point on the coastline. And then this distance is root 7 minus x squared plus 1 squared, right? Given that on that triangle, this side 7 minus x, that side's 1. Okay, so let's clean this up a little bit now that we got it. So that's going to be 49 minus 14x, okay, plus x squared, whoops, plus 1. Okay, or let's just say x squared minus 14x plus 50. All right, so there are those distances along the water and along the land. Now, I want to minimize the time, the overall time to get from here to there. And the time will be the distance over the rate. I've got the distances, and I know the rates are both 4 miles per hour. So here goes. T, time, is going to be, in the first case, along the water, 4 miles per hour to travel this distance. Okay? So that will be root x squared plus 4 over 4. That's the time for this leg of the journey. And then the time for that leg of the journey. Well, same idea. We take the distance over the rate. So in this case, I'm going to get root x squared minus 14x plus 50 over 4. Okay, so I've got those then. All right, I got that the way that I want it. Now, we need the derivative of this. Okay, all right, so t prime. Now, you can use the chain rule to find the derivative of each of these. And the derivative that you're going to get, where I'm gonna save a little time and space, because I think at this point you can probably find the derivatives. If you have trouble with this part of it, then you can ask me, but it's x and 4 and root x squared plus 4. Okay? All right, for that one. For this other one, it's going to be x minus 7 and 4 and root x squared minus 14x plus 50. All right. Okay, so there's t prime. Now, I wanted to minimize the time to travel from here to there from the beginning. There's a function that tracks the time. There's the derivative. It would only be a matter, if I wanted to find the minimum, to find the derivative and where it's equal to 0. Okay? All right, well, I've got the derivative. Setting it equal to 0 is going to involve something like this. Okay? If t prime is equal to 0, then that will give me x on one side over 4 root x squared plus 4 equals to negative x minus 7 over 4 root x squared minus 14x plus 50. Okay. And at this point, I'll multiply, cross multiply. All right. So if I cross multiply, I'll get 4x over here negative root x squared minus 14x plus 50. Okay, this going over there. Well, I'll send the negative over there too. And then on this side, I'll get 4x minus 7 root x squared plus 4. Okay. All right, now two things. The 4's cancel, right? Because they're identical on each side. So let's do that. Let's do that. Okay, so the 4's are gone, and I'm left with this. What else could I do to solve it? Well, so I've got these roots there. I'll square both sides of the equation to get rid of that. Okay, so I'll square both sides. Here, I'll get x squared, and then with the root, I'll get x squared minus 14x plus 50. And then over here, squaring each of these factors, I'll get x minus 7 squared. And then here, x squared plus 4 root squared is going to be x squared plus 4. Okay, so that's what I get then after that part. Now this, if you do all the multiplying, it turns out to just be a quadratic, all right? And so it's going to take some multiplying, etc. I'm going to leave that up to you because I think if you're careful, you can do it. You know, if you get stuck, you can ask me for help. But say you multiply all that out and you combine like terms and you do all that sort of stuff that you do with those kind of equations. Here's what you're going to get. 3x squared minus 56x plus 196 equals 0. And we'll solve that by the quadratic formula. And that's going to be the negative b plus or minus root b, you know, that whole thing. And the answer this we'll get is 12 1/3 and 4 2/3. Okay, well that one is too far out. You know, these are only 7 miles apart. And I'm wondering where this point is. Okay? So it can't be 12 1/3 miles. 4 2/3 miles, and that it could work out that way. All right? So that's my answer. This point right here, Where should this point be? Where should you dock on the coastline to get from here to there the fastest? Well, that point should be 4 2/3 miles this way. Okay, so 4 2/3 miles. Now, so let me give my answer. I'm going to put it up here. So I did all my work, and I'll get that from the quadratic formula. But 4 2/3 miles will be my final answer. And I wanted to put that up with the picture because that's how I was phrasing my question, was by reference to that picture. All right. Well, so this one, that's the kind of the peak of the problems I was going to do in this lesson. Maybe, well, not maybe, definitely the algebra is harder, but I still aim to do the same things. I have to express what I'm trying to minimize or maximize as a function. You want to get there the fastest? You need time to be equal to something. You need time to be a function of something. And then you find the derivative of that function. You set it equal to 0. You solve it through whatever kinds of crazy algebra you need. And then, well, you can interpret your answer from that. Okay.